apply. I have to say I'm worried a little bit by the term template reaction because I don't know, we've got lots of other templates running around, but let's see how it works. Chemical reaction template, chemical reaction. I mean, it's really okay. Let's see how it works. Okay, so this is some kind of smarts string that represents that reaction, which we are representing like this. And our full form for this is molecule pattern. So what does molecule pattern mean? Where's the pattern part of molecule pattern?
Right. So it looks for, so it's a substructure pattern. It describes a subgraph, a substructure in the molecule. So this one, it would be just a COO with a double bond in there. And so it, yeah.
So this is a piece of graph rewriting, basically. Do we have any of the people here who know about graph rewriting, who've worked on graph rewriting?
I have. Not with our code, though. I don't know the details under the hood for graph, but I've done graph rewriting.
No, I understand, but people, I mean, the physics project is full of graph rewriting.
Oh, we don't have anyone here.
Okay, so we need somebody from that. I don't know if I don't know if Nick will be available or James.
But Jason, you had discussion with the graph people, right?
No, but there's two different graph groups. There's the graph theory group and Charles Poo. That's one group. And then there's the people who've worked on the physics project, where we have a boatload of WFR functions, which are slowly getting worked towards finalization. Okay. Nick Merzen will be the most relevant person. I don't know if he's awake around at this time. Maybe Corey could go and check that, please.
I just pinged him.
Okay, and if he happens to be available, it'd be great if he joined. Okay, so the problem here is that you've got a completely new and different way of representing pattern variables here than any other part of the system, right?
Correct.
Okay, so that's not going to work. Period. End of story. I can tell you right now, it's not going to work.
I think the use of the word pattern variable is a little bit misleading. Because it isn't really a pattern variable in some sense, I would argue.
It's a pattern atom. No, I mean, what you're saying is, if there's a molecule that has a little piece that looks like this, then okay, let's try to understand what this is. So this means, oh, Nick is here, great. Okay, can you explain to me what this, can you show me an example where, I mean, this is simply the template. Can you show me the template in use?
Open the esterification section, please. First, the intermolecular one there. The first example down a little bit is acetic acid plus ethanol. And in the box shows it all drawn out.
Okay, so hold on. So this is saying, I don't really understand what's happening here. So the question of indicating where the pattern variable, I mean, so we start with this molecule, yes?
Right, that's acetic acid, and that matches the first.
No, I think that's not. I think that's not what Stephen means with the question. We have this abstract representation that says, as long as you have something that has this and something that has this, then we can do this. And then there is a bazillion of different things we can apply it.
Yeah, it's just like the physics project. It's just like what we have to do there, right? So we've got this thing where there are two oxygens, one of them is connected with a double bond, right?
Right. And
so what that means is this thing here, that piece there, matches that, right?
Yes.
And there's one possible match in this particular case.
Correct.
Right.
And in principle, there could be two matches on this molecule for that graph fragment, right?
Yes, that would be the second example. The one with sorry. Did you put in multiple The other one is with the multiple matches with the OH.
Right. I mean, there will be multiple match examples, but just to focus on the one.
Yeah. Okay. So this is really, really, really directly analogous to what we're doing with the physics project. So now the issue is always, okay, so the question is, how do you re-glue pieces of the graph? Do you understand the question?
Yeah.
So we have that piece of the graph. We're taking that out. And how do we re-glue it?
So
there's numbering on the left-hand side and numbering on the right-hand side, which says how do you have to re-glue.
right, and so any part of your input molecule that wasn't matched by the pattern but is bonded to one of the atoms in the pattern, that bond and all the atoms attached to it are brought over to the products.
The addressing on the re-gluing, the rewriting, is handled through the atom map numbers. They are the atom map number options in the Wolfram language form, and it's the digit or the integer that follows the colon in the reaction smarts. And there's generally a one-to-one from left to right.
Okay, so turning on Nick here, do you see? Okay, so like if we have like Wolfram model type things where we've got named atoms of space in that particular case, which don't have an, okay, so the difference with what we have in hypergraph rewriting is we don't have a tag like this is a carbon atom. We just have the name of that atom of space. And we don't have a notion of like double bonds and so on. But otherwise, I think it's the same. Or am I missing something? Nick,
It is the same. That example that I did using graph and rewriting stuff, but not able to use attributes, annotations in graphs, it basically demonstrated that. I managed the annotations on my own to do the matching.
Okay, but okay. So wait a second. So we've got 3 different projects that are all doing something very similar. We've got the whole Wolfram model hypergraph rewriting stuff. We've got a potential project in the graph theory area doing generic graph rewriting, and we've got this project. Is that correct?
As far as I know, yeah.
And what about the trees people? Do they have yet another project doing tree replacements?
I'm not aware of anything there, but they could. I don't know.
I think there is stuff there. Sorry, Nick, did you have any comments about this and how it relates to the graph rewriting we've done?
Well, looks very similar. It's like it can be, I think like all of this rewriting can be just expression rewriting with some, I don't know, additional rules. I think all of this can be just a complicated tuple replacement, subset replacement thing. So
I see what you're saying.
Yeah.
But so the issue here is the awkward thing. Okay, I should have got another chemistry question. Are these arrows always one way?
For this data structure, yes. I mean, in a real reaction, I mean, you would have that reaction and its reverse existing in equilibrium, oftentimes.
But the equilibrium could be very much to one side.
But the way that these template reactions are set up, and I'm open for a different name, but just the patterns on the left can be very open-ended. That you can say that the atom number 3 can be a chlorine, it can be a carbon, it can be a bromine, but that kind of thing would not be present on the right-hand side. On the right-hand side, you say that atom is what is something
whatever
specific.
It was. Right. It's like saying it's exactly analogous to saying on the left to saying something like, you've got a pattern of the form X colon, and then it's, carbon or fluorine or whatever, right?
Yes.
And then, but on the right now, that goes to some f of x,
Okay.
right?
Right.
Yes.
Okay. Now, yeah. So I mean, the thing that would to me seem much better. Okay, the molecule pattern construct. Do we already have that or not?
Yes.
And what does it do?
So let's see. I mean, you can use it in a molecule plot to highlight a substructure. It can be fed to find molecule substructure or test, or there's tests for its presence.
Okay, but so what it does right now, it doesn't have named variables, correct?
Correct.
Okay, so what does it represent? So it represents a subpart of a molecule right now.
Yep.
Without any names.
Yes.
Right.
Okay, so the subparting of a molecule. Okay, for a molecule right now, the only way you can identify the subpart is through essentially its tagged graph structure. And by tagged graph structure, I mean, it's got it's got types for the atoms, correct? And it's got types for the bonds as well. What happens if there's stereochemistry?
So that gets lumped into an option in a molecule. It will be added to molecule pattern, but we don't have a pattern for that at the moment. It's like
so fundamentally the stereochemistry. So what we've got here, the molecule pattern on the left is identical to the one on the right in the sense that we can think of it as just a subgraph with name tags and so on. But then the new thing on the left is we've got to name parts of the pattern that we are matching to be used on the right-hand side. Correct?
Correct.
And I don't understand why we're not just using a mechanism that is, why don't we just use the pattern matcher? I mean, why don't we just say here, okay, to rewrite this, okay, let me rewrite this. And I understand there's one issue here, but I'm going to rewrite this anyway. Okay, so let's say we forget this, okay, and we're just basically saying X colon this, forget that. It's Y colon this. And then we go on the right-hand side, arrow, and there's no atom C anything. It's just X, if that's what you want it to be. You get what I'm saying?
Pretty much. Sometimes the formal charge on an atom may change, or it might end up being a radical and have an unpaired electron.
Okay.
So we have to account for that as well.
Yeah, there could be
and this is where the stereochemistry could come in also.
Okay, but fundamentally, in our language, the representation of, I mean, we also have to think about when we do a graph pattern.
And we probably want to go back and forth between smarts. And if smarts have the number labeling, we must somewhere preserve them.
Right. And also, I mean, so we definitely were thinking about these lines. I mean, so I mean, we could write them as patterns like this. And I would, I mean, we do not use the pattern matcher to find substructures inside a molecule. So it would have to be parsed and yeah,
I understand.
But one of the things that really struck me is, say we are generating reactions from a list of these smarts type reactions. How do we come up with the X, the Y?
Yeah, I know.
Okay, so that was
that thought, right? So probably what we would have to do is use some, I'm not sure. I mean, we could use a letter-like character followed by a number. I mean, that would be one way to do it. I'm not sure I like that, but that would be one way to do it. I mean, like for example, let's say
I think there would be no go because unavoidable it would live in global, which is off limits.
I see what you're saying. Well,
I agree. The atom mapping numbers do seem very counterintuitive, especially when you see them written out like that. In the end, I feel like this thing is it's going to come into its own when we're able to draw these or to take an actual fully fledged chemical reaction and create a template reaction by chopping off bits and
Yeah,
assigning.
okay. Let's ask this question. I don't know the answer to this. If we this object pattern, does it allow us to have what does it say about its first argument? So it says its name must be a symbol. I wonder whether the parser thinks that.
Yes, I think so.
Well, it certainly does in the case where it's X blank.
I don't think you can make a compound, it will not work properly.
What do you mean? So you mean if I say
X
pattern,
of one column.
no, but if I say this, something like this, I wonder if that works. If I say that, if I say f of that, well, this is probably going to be very unhappy. I can't imagine that's going to work. And now I say f of okay. Okay, so let's go back here. All right, let me just think for a second. So when we think about graph rewriting, for example, let me show this example. Where is it? Here we go. Okay, so this is a typical piece of graph rewriting. I don't know what that. Oh, there we go. Yes. So, I mean, this is hypergraph rewriting. Okay, so these are names of atoms. These are pattern names for atoms, which we have sloppily not had as X blank. I think we have a version of this where we do include the X blank. Nick, can you comment on that?
Oh yeah, there's some function that converts rules back and forth, like pattern rules, something like that.
Right. But so let me just compare and contrast this kind of rewriting with what we're doing over here. Okay, so here we have names for the atoms, but no tags for the atoms. Am I making sense?
Tags being the other properties of the atom, that sort of
Well,
stuff.
things like it's the fact that it's oxygen.
Yeah, okay.
Okay. In addition, in this case, we have, I mean, this happens to be just a graph, which is what you have here. And you also have tags for the edges here. That is the double bonds, for example.
Yep.
Okay.
Yeah, I tried to write reactions with these hypergraph rewrite rules 2 years ago, and it just did not work.
Okay.
You're trying to reproduce some chemical reactions with it. And the best I could do was to use multiple edges between atoms to represent multiple bonds, but everything had to be carbon because I couldn't do anything else in terms of annotations.
Nick, can you comment from your more general functions that we used, for example, in the mathematics project? Do we have ways to effectively have more annotation of these atoms?
Well, I had a version that works for general expressions, so, and I
Okay,
can,
where is that?
like for example, multi-replace function that I had.
Okay, is that in the function repository yet?
Yeah, I'm like in the process of revising it, but the old version is there, and this function has an ability to have a left-hand side that acts on a 3 separated expressions, right? So it has, if it's a list, if the left-hand side of your rule is a list, then it searches for both of them, and it can map at multiple positions at once. And then it's just a matter of how you splice it back. And for a list, I have like a special rule that it actually uses splice. So we can somehow create a rule that acts exactly like hypergraph replacement, but
I
for
see.
general expression.
Maybe you should explain it. We should go through this in more detail because I think this seems highly relevant. Do you believe that you could write with multi-replace, you could actually write this template, the reaction apply function? Does it seem that you could?
Well, I think so, yeah. I don't see an immediate problem with that.
Okay.
Maybe there's a gotcha there, but not sure.
But so in that case, how would you represent the templates?
Oh, if it's a graph on the left-hand side and on the right-hand side.
Right, but the problem is the
edges.
naming of the nodes. Yeah, the problem is the naming of the nodes.
Well, you can just have like any expression that has a name in it, and you just have a pattern that matches against this name.
Can we do it more explicitly? Could you give a suggestion for what this would actually look like? So in this case, we've got.
Well,
Okay,
if you like, take
go
this
ahead.
multi-replace example that like the third one that does a tuple replacement, and your expression is a list of like expressions, the xy. In this case, it would be a list of bonds, and your left-hand side would also expect some like just edges, meaning vertex goes to vertex, and you can replace it with new vertices.
Okay, but let's be explicit. Go ahead.
One difference with, for example, using the esterification reaction where we were looking at. So you have two oxygens, so they're both oxygen, but they are connected differently to the carbon in the carboxylic acid component. How are you supposed to do that with the multi-replace?
What are you pointing to, Jan?
The esterification reaction. Go to the one at the very top of what you're looking at now.
Here?
That one, yes, that one. So for the first pattern, carboxylic acid pattern, you have two oxygens connected to a carbon, but they're connected in different ways. So I mean, you have vertices with the same label, but have, for lack of a better term, different environments. So how are you supposed to do that with the multi-replace?
Well, I mean, this here, that's cute that you can get it to light up like that. That's.
So I'm glad you're like, I haven't sent that to design yet, but yeah.
It makes one wonder whether we should have that happen for patterns in general. Wow, interesting idea. That if you just have a pattern, you know, that's a suggestion for user assistance.
It would be nice to be able to visualize complicated patterns very easily.
To visualize general patterns like f of x.
Yes, general patterns, not just this one.
Yeah, right. Okay, but anyway, so what you're saying is, let's take a look at this. So this is so unbelievably similar to a token event graph situation where you've got this piece and this piece. Okay, Nick, do you understand what this is doing? Do you understand the chemistry? I mean, let's take an example of where this is used. Okay, so we've got, where the heck is the molecule? Okay. So in this case, this pattern matches one molecule. This pattern matches on a different molecule, right? These can't both match on the same molecule.
Correct. The way this is written, that's true.
Yes.
So that's kind of the meta logic of the chemistry, is that those have to be on different atoms. Is that generally true of all?
No, no, it's not generally true. And we have examples further down in this notebook where we show that. You can do it either way. And you can make it expressly one way or the other.
Okay, so I'm a little bit confused about the physics of this. Okay, so we got two molecules bouncing around, and they're going to crash into each other, and there's some exchange of bonds and so on.
Yes.
But how can that happen? There's no, if it's a self reaction, so to speak, that can't happen, right?
But it's to be long and
it's actually more like
molecules are flexible.
Yeah.
Okay,
and
all right,
one
all right,
end
all right.
can reach around,
okay, fine.
like the snake biting its tail.
Yeah, okay, fine. All right. And that really happens.
Yes.
Yes, intermolecular reactions are actually more likely to happen than intermolecular ones.
Yeah.
Because the flux of, because the things are guaranteed to be right there.
Correct.
Okay,
Yes.
so what's a famous example? You see, I've been reading Teo's book about chemical reactions. I haven't got to one like that yet. What's a famous example of a snake biting its tail type reaction?
This one too. There's an intramolecular version of esterification. I think
It's further. It's down in the exam. Yeah, it's further down. I don't know of a famous one, but it
does biology use molecules biting their tails a lot?
It happens.
Yes.
Cyclizations happen in the
what is it called?
Environment.
Cyclicization, right? So you're making a cycle. I mean, speaking of rather large ones, right? So we have we represent circular peptides and DNA and everything.
Right.
They're quite common.
And it's made linearly, and then the ends are stitched together.
That's what you say. Yeah, well, that one I've certainly heard of. But those are okay.
The lactonization is the intramolecular version of what's happening here.
Right, and
we need functional groups.
Sorry, I wanted to say that we need a way to visualize the fact that in that template reaction, those two pieces are listed as disconnected parts of the same graph on the left-hand side, like the same molecule.
As opposed to the plus thing.
Exactly.
Right. I guess the lack of a plus is the, although I think in the end, a frame around them might be good.
Okay, but in the smarts version, how is it represented? That's a plus and the other one isn't.
There's a dot.
With parentheses. Well, the dot for the two disconnected parts, but parentheses around the whole thing says that it's intramolecular. No parentheses says it's intermolecular, and parentheses around the part to the left of the dot and parentheses around the part to the right of the dot also means that it's intermolecular.
Okay.
I'm just trying to emphasize ter and tra.
Yeah, so I got it.
So,
yeah. Okay. All right. So interpret this. Nick, do you have an interpretation of this? Gosh, what the hell is going on here in the intramolecular case? So in a token event graph, these are just two tokens. No, I'm confused here.
In the token event graphs, those would, for the intermolecular case, they would be two tokens. In an intramolecular case, the rewriting would be done on a single token with by one of the rules.
But I thought that the thing that I'm confused about, each one of these pieces is a token, I think. Like
in this case, yes.
No, I understand. But in the other case, those two pieces, the head and the tail can be anywhere on the molecule.
Yes.
Correct.
So I don't understand. I mean, okay. In the physics case, this is like the standard case. There are two pieces of the universe, where the universe is a molecule, and they are combined in some way. Okay.
Yep.
But and what this is doing is it's saying they combine in some way, but then you break off a new universe that is quite separate. So I mean, in other words, in Nick's case here, we've got a single expression that is being multi-replaced by a rule. It seems like this is a case where, and that's the case here, a single expression where there's a rule being applied.
Yeah, and it would have to be on we would have to follow the third example there where we've got the list of XYY or XYXY. We would have to have an expression that has a list of atoms and a list of bonds, and we would be rewriting those lists. The other expressions, the f of x, g of y one, we can't represent molecules that way because those are strictly trees, and we need to be able to represent cyclic structures.
I get it. So my question here would be, can you give me an example where we can nest a template, a reaction apply? I just want to see what it looks
repeatedly?
Like. Yeah, you do it. Make a dendrimer, for example. Can you make a dendrimer?
The closest thing we have in this notebook here is taking a fatty acid and breaking each of the 3 esters in it one at a time, but doing it in a fixed point operation. The saponification section.
Right. So basically something like nest list or fixed point, we should be able to iteratively build dendrimer like what you're asking.
Down a little bit further.
So am I wrong, Bob, in thinking that we will see some examples more along those lines in the next meeting?
Let me check my notebook to see where that went.
Okay. We do have another meeting with a very similar set of invitees.
Okay, I think we're gonna. I mean, this is a complicated problem that you're describing. I mean, this whole thing. What is this? What is that? Is that different cases of different ways?
Those those are all the different products that you can come out using a given set of reagent, a given set of input molecules, and a given template reaction, because the patterns matched both reactants in different ways. And in this case here,
what a beautiful multi-way system story.
Stay tuned.
Yeah,
so,
I mean,
in theory, you can have all of those. In practice, only a few of those will actually exist due to certain rules.
And what's the typical reason they don't exist?
Like the result is too strained, or the electrons do not interact right, so they have to be in this kind of position relative to each other.
And can we detect that failure, or is that beyond what we can compute about these molecules?
That's actually a good question. What do you think, Jason?
If we've got 3D geometry, we can do a lot of it.
Okay.
It's a bit of a stretch with just the topology.
Yeah.
Okay.
Okay. The example I was looking for is this section called tricaprol glycerin, and I think that one has been removed from this notebook.
Okay, all right, fine. You know, the thing that's so crazy about this field is that as we were saying at one time before, right, if this was particle physics, I could rattle off all these weird names of, you know, saponification and all this kind of thing. But I don't know that for chemistry. Unfortunately, I learned it for something much less useful than chemistry, because, you know, particle physics is much less accessible, at least in this century, than chemistry. But it's just, I'm sorry, that's just an editorial comment about the fact that each one of these things is a kind of a personal friend for people who know chemistry.
Exactly.
Yes.
And one day I should learn all this stuff. I got back, by the way, we're going to play around with the Emerald Cloud Lab. I mean, I got back a long thing from Brian about that. And
okay.
He's proposing that we try and I mean, have you guys looked at their actual documentation, by the way? They now have detailed documentation online for all their, you know, I looked at the one for their HPLC machines, and it's a huge long piece of, you know, lots of Wolfram language code for how you determine, you know, whatever they are, buffer solutions and who knows what else that you put in the machine.
I've seen a preliminary version many months ago, but if they've updated, then we haven't seen it.
Okay, well, anyway, I'm going to try. I mean, my silly little project was going to be to try and measure, what are they called, flavonoids in the chocolate
Yes.
that I eat.
Flavonoids, yes.
Yeah, just as a first step in using their technology stack. I mean, clearly not the most profound thing to try to do, but at least it involves, you know, getting some sense. I mean, that the claim is that that should be easy. So,
Stephen, could you forward me Brian's reply, please?
Yeah.
Thank you.
So we will need another meeting here because we didn't really make much progress on this one.
We will definitely need another meeting. This is a complicated issue. There's a complicated area, complicated issue. I mean, what you're doing here, I mean, you know, the primary design issue here is how to represent named pattern variables, I think.
Yeah.
And a secondary issue is this thing that I don't fully understand yet, which is, are you pulling in two universes? Is this a clash of universes, or is it something that happens within a single universe, so to speak? And also the one thing that is a little different, okay, between actually this is a very interesting point. A big difference between what you're doing and what we've been used to with graph rewriting is, you know, that oxygen has to land up somewhere. There's conservation of atoms, which there is not in our, for example, in our hypergraph rewriting. There is no conservation of atoms.
In real chemistry, there is conservation, but these rules can be written without conservation, and a lot of times practicing chemists do that.
Because you don't care where a certain stuff ends up, you care about certain things, right? You don't care about the whole picture.
Well, that's careful there. There is a caring about it. It just may not be necessary for the conversation.
Getting your point across, yes.
Correct.
Hold on. What would happen if one of those oxygens was missing on the right-hand side? What does it mean?
So the rule basically for this is if an atom has a pattern attached to it, if it has a mapping number, then it must appear on both sides of the equation. If it doesn't have one, then it can disappear, and it's just
it goes off into the solution or something like that.
Yeah, chemically that's what happens, and oftentimes, you know, for the esterification, they don't worry about what happens to that water molecule that you thought, you know, that you had said was, oh, this is another universe that we've just created.
But you just care
that's
that you
just
created
ignored. They know it goes off into solvent.
Right.
Unfortunately, if you want to pay attention to the energetics of that process, you can't let it just disappear.
Yes, that's right, Jason. You know,
so
detailed.
It's a case to case. It's a case to case basis. Sometimes you want to pay attention to the water, sometimes you don't.
Okay, and so what on earth would that mean? Let's see. For us, when we have a pattern transformation and the pattern variable doesn't appear on the right-hand side, that's cool. I mean, we don't care. Just means there's no conservation of matter, so to speak, in that case. There's no conservation of expression fragments, which is fine. But you can't have something where it appears on the right but didn't appear on the left. Correct?
Yes, definitely.
Okay. So, I mean,
you can't like pull it out of the solvent or something. You can't.
Jason, we could do that, can't we? I mean, we just don't attach an atom map number to it right now, and you can make extra atoms appear.
Right. I mean, in general, these can be used to model actual chemical reactions, but a lot of the reactions that that I find in the wild, meaning on GitHub and like when I search for these things, reactions written in that string format, they are just concerned with trying to let's see, they know a big, long, complicated synthesis that involves many steps, but in the end they can boil it down to some functional group gets converted into another one, and there are lots of intermediate processes, but I'm just looking to generate a list of molecules that could be potential candidates, and so that are potentially makeable. And so I just write down a reaction smarts or some reaction expression template that goes from step 1 to step 20 and skips everything in the middle. And so in that way, these can be really general, but that's why we would have things like reaction balance Q and other things to really verify that you want the thing to be physical.
Right. Okay, we are unfortunately running out of time here.
We will sending this to Nick then and discussing with Nick
we will actually, there's comments here from Dongs on a live stream. Oil and gas does reforming to make rings, which upgrades gasoline octane. Oh, I see, that makes sense. For example, N-heptane might be reformed into toluene plus extra hydrogens.
Yeah.
And polymerization can be expressible as nested reactions. Yes, I mean, I agree, as you're adding a little piece onto the end. All right, we have to wrap, unfortunately, right now, but we will be continuing. And for folks on the live stream, bye for now.